Hi, I'm Tim, and this is the first of a series of videos about anti-gravity matter. There is no gravitationally attractive dark matter. Instead, the universe contains a thin atmosphere of anti-gravity matter. So we're assuming that anti-gravity matter is made of particles that have positive mass. They're repelled from each other, and they're also repelled from normal matter. That is to say, planets and stars and me and you. And we assume that anti-gravity is like gravity, except that it operates in the other direction, and instead of using the gravitational constant g, we use A subscript A for repulsion between anti-gravity matter particles and A subscript n for repulsion between anti-gravity matter and normal matter objects. There's an interesting point to make about anti-gravity. It's not exactly the opposite of gravity. In an anti-gravity field, normal matter and anti-gravity matter accelerate in the same direction. But in a gravity field, normal matter accelerates in the opposite direction to anti-gravity matter. So anti-gravity is not exactly the opposite of gravity. Electromagnetic radiation is also repelled from anti-gravity matter, and we assume the constant AN for that. And these repulsive forces are similar in strength to the reverse of gravity. So AA seems to be approximately the same as AN and seems to be approximately the same as G. Anti-gravity matter particles only rarely interact with normal matter particles except by gravity. They do occasionally interact with normal matter particles, and that becomes an important point later on. And of course, there's an enormous amount of anti-gravity matter in the universe, and it's spread out throughout interstellar and intergalactic space to create a thin atmosphere. The atmosphere acts like an ideal gas, and it has the bulk properties of temperature, pressure, and density. And as a result of the expansion of the universe, most of the anti-gravity matter is very cold, but it can get hot. So anti-gravity matter is spread out fairly evenly throughout the universe, but it's repelled by normal matter objects. This creates a region of reduced density and zero density around, for example, a star. And here's a bit of terminology. Any region of space that has a density of anti-gravity matter that is lower than the background density, we refer to as an AGM lacuna. An AGM lacuna attracts normal matter objects and anti-gravity matter particles and electromagnetic radiation. This is due to an unbalanced lack of repulsion. So lacunas can also be caused by currents and flows of anti-gravity matter and also by regions of hot anti-gravity matter. And all these different types of lacunas attract normal matter, anti-gravity matter particles and EM radiation. Anti-gravity matter is not the same as antimatter. So here's a concept comparison. This is the concept for dark matter. With dark matter, we imagine that there is a cloud of dark matter that collects around a normal matter object, and that increases the normal matter object's apparent gravity field. Here's the anti-gravity matter concept. There's anti-gravity matter spread out throughout deep space, but it's repelled from a normal matter object, creating a lacuna, and the lacuna causes an apparent gravity field that adds to the attraction of the central normal matter object. It's a double negative effect. There's the AGM lacuna, and here's another bit of terminology. The boundary within which there is no anti-gravity matter is called the AGM boundary. So now we're looking at the density profile of anti-gravity matter around a central normal matter object. And this is a simple case where the anti-gravity matter atmosphere has negligible or zero pressure. And in that case, we find that there is a step change in density of anti-gravity matter around the normal matter object. The second graph shows the acceleration of a small normal matter object due to the gravity of the central normal matter object, and this just follows the inverse square law. The third graph shows the acceleration of a small normal matter object due to the attraction to the lacuna. And what we see is that the attraction increases linearly with radius up to the AGM boundary, and then it reduces with the inverse square law. So here are some estimates of the parameters of the anti-gravity matter atmosphere. DAB is the background density of anti-gravity matter. DAB, I'm currently estimating, is about 2 times 10 to the minus 19 kilograms per cubic meter. In this hypothetical situation, if anti-gravity matter pressure was 0 or negligible, the Sun's AGM boundary would be at about a little over a light year. On that scale, you can see that the solar system and everything in it, including all the way out to the Voyager probes at about 160 astronomical units, would all fit within the ink of the y-axis on the bottom graph. The change in gravity within the solar system is minute. Even out at the Voyager probes, the AGM lacuna would only increase the apparent gravity of the Sun by about 1 part in 10 to the 8. So this situation where you can neglect AGM pressure is referred to as the anti-gravity dominated situation. You can see bottom right that the total acceleration due to both gravity and anti-gravity is gm over r squared, and then that lot in the brackets there. Now the lot in the brackets is constant, and what's more, if g equals an equals aa, the contents of the bracket equal 2. So in that situation, the anti-gravity matter atmosphere would double the apparent gravity of a star way out beyond the AGM boundary, but have almost no effect on the gravity of the star close in the solar system. So this is a different case. This is where AGM pressure is not negligible. And what happens is that the pressure pushes the anti-gravity matter in closer to the central normal matter object, and it takes on a profile as shown in the top graph. The gravity of the central normal matter object is unchanged, and the attraction of the AGM lacuna is unchanged very close in and unchanged very far out, but around about the region of the original AGM boundary, it's much reduced. So current best estimate is that if there was nothing else affecting the Sun's AGM boundary apart from AGM pressure, then the Sun's AGM boundary would be at about 1/10 of a light year out. And this situation is referred to as being AGM pressure dominated. So I'm going to leave it there with some terminology, some of which I've introduced already. DAB is the background density of anti-gravity matter in the universe. PAB is the background pressure of anti-gravity matter. And AGM lacuna, any region of space with a density of anti-gravity matter less than DAB. AGM equivalence is the principle that you can treat a lacuna as being a gravitationally attractive object, which simplifies calculations quite a lot. The AGM boundary is the boundary of the region of zero density anti-gravity matter, and AGM pressure dominated and anti-gravity dominated are two behaviours of anti-gravity matter around a central normal matter object.